All right. Last thing we have from this section is example 3, where we are asked to determine the following limits, use your intuition, and numerics. So for this one, I'm going to be a little bit more relaxed on the numerics. I hate doing lots of tedious arithmetic calculations. Let's face it, that's what machines were invented for, not us. We got bigger things to think about. So for these, we're going to use a more holistic approach. So the easiest way to evaluate a limit is graphically, to a degree, as long as your graph is accurate and you can read it properly. So here, we'll graph this function 1 over x. 1 over x looks like this. There's a vertical asymptote at x equals 0 where we divide by 0. So here we can see that the left-hand limit, so as x approaches 0 from the left of 1 over x, this is negative infinity. And the limit as x goes to 0 from the right-hand side of 1 over x, this is positive infinity. And although each of these are infinite, positive and negative infinity are not the same. So this implies, so I'll just say together, these two imply that the limit as x goes to 0 of 1 over x does not exist. So that was a purely graphical approach. Another thing we can do that's a little bit more numerical is if we do a left-hand limit, we should be plugging in values to the left of 0. So think about plugging in like negative 1/10, negative 1/100th, negative 1/1000th, something like that. Well, what do we know about dividing by a really small number? If you divide by a really small number, that makes the overall fraction very, very, very big. And if we divide a positive number, like 1, positive 1, we divide that by a negative, positive divided by a negative is a negative. So we can see that for the left-hand limit, we're guaranteed a negative because if you're, that's the definition of negative. It means you're to the left of 0. So we know that we have to get a negative. And if we approach 0, that means the numbers that we're plugging into the denominator are getting smaller and smaller and smaller. So that means our answer should be a really, 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 really big negative number. Well, if we just continue that process of shrinking the size of our denominator, then the fraction just gets bigger and bigger, as big as we'd like. So the trend is this plunges down towards negative infinity. And then you can make a similar argument for what you did what you would do for the right-hand side. And now using some intuition here, let's compare what we're being asked of in part B. In part B, we have, again, the limit as x goes to 0, and we have a really similar function, but not identical. The function is 1 over x squared. So sure, they're different, but if we still have a vertical asymptote at x equals 0, so we still have that. But because the denominator never stays negative, because when we plug in a negative value, it gets squared and becomes positive. So effectively, we take our previous graph of 1 over x, and we just draw it like that. So now what we end up seeing is that the left-hand limit of 1 over x squared equals positive infinity, and the right-hand limit of 1 over x squared also equals positive infinity. So this implies that the limit as x goes to 0 of 1 over x squared equals infinity. Now there's a little caveat here we have to be careful of, and that is the definition of a limit, the true definition of a limit, says that a limit exists of an expression if that expression approaches a unique real number. So like, let's look up here in the previous example, example 2. We checked our two different approaches, left and from the right, and we see that it's approaching the real number 6. Same thing for part B. If we look at the piecewise function we had in earlier videos, we can see that over here, the left and right hand limits at x equals 2, each of them do approach a real number. Each of them yield an answer, 4 and 5 respectively, but that value is not a unique number. It's not the same number, in other words. 4 and 5 are different numbers, so the limit doesn't exist. So it has to be, you have to get the same value no matter what approach you make, but also it has to be a real number. And that's where the little caveat comes in down here. In the previous 3a over here, because they approach different varieties, let's say, of infinity, the limit didn't exist because they didn't match. Whereas over here, they do match now. They both yield positive infinity. The issue now becomes that infinity is, sadly, not a real number. So because infinity is not a real number, this technically also means D and E does not exist. But you won't catch many people writing D and E here. Why is that? Well, because when you read this infinity symbol in the context of a limit, what you should actually read in your head is this limit does not exist, and the reason why is because it's approaching infinity. So feel free to write infinity. It's going to be useful. A lot of times it is useful to know if something is getting very big. So that's why we'll do that.